Fisher projections, first of all, they reveal planes of symmetry fairly easily. Okay, so planes of symmetry are easier to detect in the eclipsed formation. And remember, that's what we have with the Fisher projection. We've got the structure as it looks like in a eclipsed conformation. So this is an advantage of the Fisher projections. Okay. Now remember that the plane of symmetry is important because if you have a plane of symmetry, then your molecule overall is not chiral. You might have chiral centers in the molecule, but overall they cancel each other out if there's a plane of symmetry, and it will not be chiral. So we've got some examples here. And what we want to do is identify the chiral centers in each of these molecules and then determine if the molecule is chiral overall. And we're also going to label some meso compounds. Okay, so let me just start at the left here. We'll work our way from left to right. Okay, so the chiral centers we'll just indicate with a little star. Okay, so for example, this carbon right here, the intersection of those lines, yes, that's a chiral center because it's attached to 4 different groups. You got the hydrogen, you got the methyl, you got the fluorine, and then the rest. Okay, so you don't have 4 different groups here because the group up top, right, with the CH3 and an H and an F is exactly the same as the group down below, a CH3, an H, and an F. So this carbon in the middle is not chiral. Okay, but the one down below is. It's got 4 different groups. It's got the methyl, it's got the fluorine, it's got the hydrogen, and then this whole other part of the molecule is considered a 4th group, and so that one is chiral. Okay, that's the chiral centers. Let's go ahead and identify any planes of symmetry in this molecule, and there is one which, knowing now about the middle carbon not being chiral, may have made it evident that you've got a plane of symmetry kind of right down the middle. If you split that molecule right down the middle, it looks the same on both sides. It looks the same above as it does below. All those are the same. Okay. Now, the other thing that we could say, it says, also label any meso compounds. This one is meso. All right. By definition, a meso compound is when you've got a plane of symmetry and chiral centers. So yes, this one is a meso compound. All right. So moving over to the next one here. So looking at our chiral centers, this carbon right here, the first one at the top, is not chiral because it's got 2 of the same group. It's got 2 hydrogens. So we're moving our way down. This one here is not chiral because it's got 2 of the same group. It's got 2 fluorines, right? It's connected to 2 fluorines, so it needs 4 unique groups. So that one's not chiral. And the same thing for the 3rd carbon, 2 hydrogens. Same thing for the 4th hydrogen, 2 fluorines. So none of the carbons in this compound are chiral, and that means it should have a plane of symmetry, and hopefully this reveals that the plane of symmetry then, is just straight down the spine of that. Okay, if it looks the same on both sides, you got the hydrogen on the left, hydrogen on the right, fluorine on the left, fluorine on the right, and so forth. So there's your plane of symmetry right there. But you would not call this one a meso compound because it does not have any chiral centers. Okay. All right, so working our way to the right here. So on this 3rd Fisher projection, let's consider each carbon to see if it's chiral or achiral. So the first carbon up here in the Fisher projection, you've got 4 different groups. You got the methyl group, you got the fluorine, you got the rest of the Fisher projection, you got a hydrogen. So yeah, I'm gonna put a little star by that one because it's chiral. Okay. All right, so what about the next one down? Well, yeah, it's going to be chiral because it's got 4 different groups. The hydrogen, the fluorine, the group up top, which is different than the group down below. So that's 4 different groups. Okay, well, what about the next carbon down? So yeah, it's also going to be chiral because the fluorine is different than the hydrogen, which is different than this group down below, which is different than the group up above, which is, they just don't look the same, right? So that's chiral. And finally, the last one is also chiral for the same reason. If you look at it, you'll see that it's got 4 different groups attached. Okay, so does this one have a plane of symmetry? Well, it doesn't have it straight down the spine because, on some sides of the molecule, you got hydrogen. On the other side, you got fluorine. So that's not identical. But if we cut it down the middle like this, then you see we do have a plane of symmetry because close to the plane, you got a fluorine and a fluorine, you got a hydrogen and a hydrogen. And then as you move further away from the plane, you got fluorine versus fluorine, hydrogen versus hydrogen. And then, of course, the methyl and the methyl on the other end. So yes, that has a plane of symmetry. And once again, since it also has chiral centers, we would label that one as a meso compound. All right. Okay, so this one, let's see. So chiral centers, well, we've got a methyl and a fluorine and a hydrogen, and then the rest of it, that's 4 different groups, so that's chiral. Here we've got a hydrogen and a fluorine and the group up top, which is different than the group down below, so that's a a chiral center as well. Okay, same thing for this third carbon. You got a fluorine and a hydrogen and a group down below, which is different than the group above, so that's also chiral. Okay, and finally, we could do the same thing down with the final carbon at the bottom of the Fisher projection there. So it's also chiral. And that there, and in this one, you can look for days if you want to, but you will not find a plane of symmetry. There's no plane of symmetry, not cutting through the middle of the molecule and not cutting down the spine of the molecule. It looks different on each side either way. So 3 of the 4 had a plane of symmetry. The one on the end here does not. Okay, now one thing to keep in mind though, and this has to do with those rules for manipulating Fisher projections, which we learned before last week, that those plane of symmetry might just be hidden. And what you do to rule that out is you do a rotation with that bottom group. Remember that when you have a Fisher projection, you can rotate the 3 groups on the bottom around without any change to its configuration or any real change to the structure of the molecule. Now, hopefully you remember what I mean by that. Let me show you. Okay, so for example, if I put the methyl group here and put the hydrogen here and put the OH group there, that's what we mean by rotating the bottom 3 groups. You can see then that the Fisher projection would look like this. So after I do that rotation, if you draw a new Fisher projection, I didn't do anything with the top part of it. It's still got the methyl and then the hydrogen on the left and the OH on the right. But now because I did this rotation on the bottom, things start to look very symmetric. Okay. And so then the plane of symmetry becomes evident. So there's your plane of symmetry right there. All right, so remember you are allowed to rotate the bottom 3 groups, and this may reveal a plane of symmetry. Here's the other utility of Fisher projections, that it's easier to draw mirror images and also easier to see the diastereomers. Okay, so mirror images of Fisher projections are also easier to draw than for other types of structural representations. So the first thing I want to point out is, remember this formula that the number of stereoisomers, so the number of stereoisomers, remember that's equal to 2 raised to the power of n, where n is the number of chiral centers in the molecule. All right. Well, in this molecule, we've got 2 chiral centers. That carbon is chiral, and the one right next to it, the carbons 2 and 3, those are chiral. So in this case, 2 to the 2, so there are 4 maximum stereoisomers. Now, for this one, we actually have all 4 of them. But for some molecules, you won't actually get the full number of stereoisomers, because if there's rings involved, they're constrained to certain geometries and things like that. But the maximum number of stereoisomers is always that 2 to the n, where n is the number of chiral centers. Okay, so I don't know, I'm just going to kind of pick one. Translate this. Well, I don't want to just translate this into a Fisher projection. So draw it like this, kind of the normal skeleton of a Fisher projection, where I've got the CH3 up top, right? That's this CH3, and I've got a CH3 down below. All right, and then over here, I'm just going to replicate what I have in this Lewis structure. I got hydrogens on the left, and I've got bromines on the right. Okay, so there you go. There's one stereoisomer. And the point of this slide is, in this first bullet, the mirror images of Fisher projection are also easier to draw than for other types of structural representation. So let me just kind of prove that. So let's say that I have a mirror plane here. And remember that the technique for drawing mirror images is you draw what's close to the mirror first and then what's far away. But I'm going to go ahead and put the skeleton of the Fisher projection in there, if you don't mind. Okay, so what's close to the mirror is bromine, and then another bromine. And then I've got the methyl groups, CH3, and then CH3. And then furthest away, I've got the 2 hydrogens. Okay, so there you go. Those are enantiomers. They are the mirror images of that, of each other. Okay, well, that's 2 of the 4. So if I want to go ahead and try and come up with the other 2, think about a different way to arrange those hydrogens and bromines. Well, why don't I just put the hydrogen and the bromine the same for the top portion, but then at the bottom, I just switch it up. I put the bromine on the left and the hydrogen on the right. Okay. And once again, I could just draw the mirror image of that. Okay. Draw what's close, the bromine, and then the hydrogen, and then the methyl up top and the methyl down below, and then what's far away. So I got the hydrogen and then the bromine. So those are all 4 of them. Those are the 4 stereoisomers. So you can see that that was pretty quick because, well, all I had to do was take the Fisher projection that I had, and I switched the arrangements on one of the chiral centers. I just flipped them, right? So it's kind of easier to come up with the different diastereomers when you're dealing with Fisher projections. That's just another one of the advantages for this technique of drawing organic compounds, particularly ones that are chiral. So another nice thing about Fisher projections is it's a little easier, I think. It's still, sometimes a challenge. This is kind of a tall order. But I think it is easier with Fisher projections to classify 2 different compounds as being identical, enantiomers, or diastereomers. Okay, so we're going to go through an example of that and get some practice with that. You'll know it's identical if all the configurations are the same. So for example, if you figure out the configuration in one Fisher projection, let's say it has 2 chiral centers, and both of the chiral centers have a configuration of R and R. And then you look at the other one, and you do the same thing. You figure out what its configurations are at each chiral center. And it turns out that they are exactly the same, R and R. That's your definitive proof that they are identical. Even if, like at that bottom carbon, at that bottom group, not carbon, but the bottom group on the Fisher projection has been rotated, you will still come up with the same configuration. Okay. Now, the other thing is that the enantiomers become more obvious, I think, when you have Fisher projections. So the enantiomers, because all the configurations are just going to be exactly the opposite. So you draw a Fisher projection and you figure out that the chiral centers have a configuration of R and R, and then you look at a different one, again, with the goal of trying to decide, is it identical? Is it an enantiomer or is it a diastereomer? Well, one sure way to find out is to determine the configurations of those chiral carbons, those chiral centers. And if they're exactly the opposite, like SS, then that's the giveaway that it's an enantiomer, that it's a mirror image. Okay. And finally, with diastereomers, it's a little bit more complicated, but it's also easier to pick out because they just have to be different by 1. So with diastereomers, at least one configuration will be the same, and at least one, but not necessarily all, configuration will be opposite. If you've got a Fisher projection with 5 chiral carbons in it, maybe one stays the same and the other 4 change. That's a diastereomer. Or you might have 4 stay the same and 1 change. That's still a diastereomer. It's just different. It's a different diastereomer. Okay, and so the example there is if you start off with something that's R and R, but then you look at the other one and you determine that its configurations are R and S, that's the giveaway that it's a diastereomer. Okay, but also another important note about diastereomers. Remember, diastereomer is a more generic term for just different ways to arrange the atoms that have the same connectivity, but it's just different ways to arrange them in 3-dimensional space. You do not have to have chiral centers to be a diastereomer. Diastereomers do not have to have chiral centers, but the rule above applies when they do. So here we've got 2 Fisher projections, and we want to identify whether we want to decide, are these identical, are they enantiomers, or are they diastereomers? So we'll start there, then I'm going to draw some more in after that. So let's look and see if they are mirror images of each other. That's kind of one test to do. So look at what's close to the mirror and what's far away from the mirror, and you've got OH groups closest to the mirror in both cases. You've got hydrogens furthest away from each other in the mirror in both cases. You got this carbonyl and a hydrogen up top in both cases. You got a CH2OH down below in both cases. So this really looks like they are mirror images of each other. So this is looking like an enantiomer. But let's prove it to ourselves, okay? So like I said, if these are enantiomers, then whatever the configuration is for these 2 chiral carbons will be exactly the opposite of the configuration of these 2 chiral carbons. So let's just figure out what they are. So remember the Kahn-Engel-Prelog rules for assigning priority to rank the groups on a chiral center. So this is, and it goes basically by atomic number. So for this carbon right here, it's attached to this oxygen. So that's going to get priority 1. Okay. So then it's attached to this carbon, which is attached a double bond to an oxygen. So that's like a carbon with connections to 2 oxygens. Okay. Where here it's connected to a carbon that's connected to 1 oxygen. Okay. So this carbonyl group wins. So that's a priority 2. Okay. I know hydrogen's going to get the lowest priority. So we'll leave it alone. And that means that the rest of this is priority 3. So hopefully you're getting some skill with the Kahn, Ingold, Prelog rules at this point. Okay, so how does this spin? In order to put those together, we go from 1 to 2, and 2 to 3, and 3 back to 1. So that's counterclockwise. But remember that when this hydrogen is coming out of the screen, and as it is in Fisher projection, the horizontal lines mean they're coming out at you, the vertical lines mean they're going away from you. So because this hydrogen is coming out of the screen, I need to do the opposite. So I was going to say S because it's going counterclockwise, but now I need to say R because of the fact that the hydrogen is coming out of the screen. I got to flip it to the opposite because of that hydrogen. So I'm going to do the configuration for the carbon down here. So the oxygen in the OH is still the highest priority connection. So that's 1. Okay. So now I've got a CH2O and a CHO bound to another carbon. Okay, so this carbon's connected to another carbon, a hydrogen and an oxygen. This carbon's connected to 2 hydrogens and an oxygen. So that means that this group up here gets second priority. And then, of course, the rest of it, this down here, gets the third priority. So once again, we go from 1 to 2, 2 to 3, 3 back to 1. So it's counterclockwise, but once again, the hydrogen's coming out at us. So I pick the opposite. So I was going to say S, but now I'm going to say R. Okay, so this one is R, is RR. All right, so now let's figure out what it is on this Fisher projection on the right. Okay, so this carbon right here, the one higher up, the OH group gets priority 1. And then this carbonyl with the hydrogen, that gets priority 2. And then the rest of the molecule gets priority 3, all for the same reasons we talked about before. So we go from 1 to 2, 2 to 3, and 3 back to 1. So that's a clockwise rotation. But once again, I've got this hydrogen poking out. So I got to flip it. So it was based on the rotation R, but now I think it's S because I got to make the opposite. I got to, select the opposite due to the hydrogen. Okay, so the OH group, highest priority, group number 1. Okay, and then this group up here is going to get rank number 2 because it's got the carbon connected to oxygen and then connected to another carbon. Whereas this one is a carbon connected to 1 oxygen, but 2 hydrogens. And so that makes it priority 3. Okay. So we go from 1 to 2, 2 to 3, 3 back to 1. So once again, that's clockwise rotation. I want to say R, but that hydrogen prompts me to flip it. So once again, it's S. So this one is SS. Okay, so that's proof right there. That's proof that these are enantiomers. Now that took a little bit longer than maybe just a visual inspection, but that's because we were looking at a pretty simple example. There are maybe situations where that is actually the fast way to come up with the answer. If you just do the configurations for each chiral center, and then, based on that, decide what they are. Okay, so for a diastereomer, I'm just going to, well, this was RR. We decided that this was RR, right? So let me just change it up a little bit. It's similar to the way I did before. So this is going to be a C double bond O with an H, and this is a CH2OH. So we'll keep this one the same. Hydrogen on the left, OH on the right. But now let's just flip the other one. Let's put the OH on the left, and let's put the hydrogen on the right. Okay, so let's determine the configurations of these 2 carbons and see what we come up with. So for this top carbon, in this one that I just drew, you got the OH, which gets priority 1. Okay, the carbonyl, the group that contains the carbonyl, that's going to be priority 2. And then all this stuff down here, that's going to get priority 3 because it's got more carbon-oxygen bonds, or pardon me, it's got fewer carbon-oxygen bonds than the carbonyl. So that's a 1 to 2, 2 to 3. Okay. So it's looking like I'm going counterclockwise, but I say, okay, well, this hydrogen's poking out, so that means I got to flip it. So that's going to be an R. Okay, so down here, the highest priority is going to be the OH. The next highest priority is going to be this this group right here because it's got the carbon connected to an oxygen. Okay, but it's also connected to another carbon, whereas down here it's got a carbon connected to an oxygen, but it's also connected to two hydrogens. So that means that it's priority 3. So we go from 1 to 2, 2 to 3, 3 back to 1. Okay, so that's clockwise. But once again, because that hydrogen's poking out, I need to change that. So it's clockwise. I wanted to say R, but because that hydrogen is coming out of the screen, I need to flip it and call this S. So this is R comma S. So that's why this one I would label as a diastereomer. Okay. And I know that because it's different by 1. 1 is the same, R and R. 1 is different, R versus S. So that's the giveaway in this case. And again, in this simple case, you may not have had to do that much analysis, but sometimes that's what will save you a lot of time if you can just figure that out. Okay, so the one last thing I want to do is I want to identify one that's identical. So what I'm going to do is I'm going to take this one. So I'm going to change this a little bit. I'm going to draw the skeleton of the Fisher projection. And I'm going to put the OH there. And I'm going to put the hydrogen there. And I'm going to put the CH2OH there. Okay, so you may have already figured out what I'm doing here. So previously, we said that this was S, and that stayed the same. That carbon looks exactly the same. So this I know is S. Okay. And we said that this one down here was also S because it was a mirror image. This one was RR, so this one is SS. So let's figure out what this configuration is right there. What's the configuration on that carbon? That's the question. Because I want to show you, I want to demonstrate how it's actually identical. Okay, so the OH gets priority 1. Okay, so then I've got a carbon connected to an oxygen, and this is a carbon connected to an oxygen, but it's also got a connection to just hydrogens. So that means that this gets priority 2. Okay, and then this gets priority 3. All right, so it's 1 to 2, 2 to 3, and 3 back to 1. So that's counterclockwise. And in this case, I don't need to flip it because this hydrogen, remember, is going into the screen. So I've been flipping it up to this point most of the time because the hydrogen was coming out at us. But in this particular example, it's actually going into the screen. So I don't need to flip it. So since it's counterclockwise and I don't need to flip it, that's a S. So it's identical. You got S, S. We said this was S, S. This one also is S, S. So even though it doesn't look exactly the same, they are identical. And the difference is, as I demonstrated, what I did was I rotated that bottom group, which is allowed. You can, on a Fisher projection, you can rotate that bottom group around.